Welcome to the Bunnyhop channel. Today we'll be going over 4 questions, 2 of which are going to be about differentiation and the 2 others about functions. So first question, find f dash of 1 if f of x is equal to log e of the square root of x squared plus 1. Okay, so this is asking you to differentiate f of x, and then sub in x equals 1 to find your answer. Okay, so to do this question, first we need to actually know some of these differentiation rules. First one would be the log one. So recall, actually I think I might use a different color. Let's see. Okay, I think a blue's nice. Alright, so recall that if you were to differentiate a log function, say log of f of x, this gives you f dash of x over f of x. Now you just have to know this. Shouldn't be too bad. Anything that's within the brackets of log, oh, I've got an e here. You just differentiate that, put that on the numerator, and put the function itself in the denominator. Okay, so there's 3 different ways to solve this question. I'll give you the first method. I'll give you is the quickest method, I think. Okay, so method 1. Alright, so for this one, we'll just be using that rule directly. So that is, if we rewrite f of x first, f of x, remember your index laws. So log e, so square root is the same as to the power of a half. So log e x squared plus 2 to the power of 1 on 2. So then, if we were to find f dash of x of that, so that means we're differentiating the square root of x squared plus 1, so that would be a half. Oh, let me redo that. Okay, so a half times x squared. This is using chain rule, by the way. Negative a half, because a half minus 1 is a negative a half. Then you multiply by the differentiation of x squared plus 1, which is 2x. Okay, and then you put this whole thing over the function x squared plus 1 square root. Okay. Alright, so that looks kind of bad. We can rewrite that. So a half times 2 is just 1. And then 2 to the power of a half is the same as just putting that in the denominator. So x over x squared plus 1. Okay, we actually don't need the brackets because x squared plus 1 to the power is just to the power of 1 here. You can see here negative a half minus a half would give you negative 1, so we just put that over x squared plus 1. Alright, so this is f. Then if we, oh, oops, okay. Right, so then if we were to sub in the value, f dash of, if x equals 1, so f dash of 1, that would give us, oops, they give us 1 on 1 plus 1, which is equal to a half. Okay, so alternatively, we could actually make this easier if we go from the very start here. Yeah, so if we go from the very start here, this section right here, we can actually rewrite this as, so that's the answer. A half is the answer, except there's other ways we can do this. So we can rewrite f of x even further by saying that f of x is equal to a half. So this is your log laws. We're not doing anything new here. So log e of x squared plus 1 to the power of a half is the same as bringing a half to the front. So a half times log e x squared plus 1. So if we were to differentiate this, f dash of 1, f dash of x is equal to a half. So you can just leave the half outside. You don't have to worry about that because it's a constant. It won't change anything. It's just a half times. So differentiate x squared plus 1, that's 2x. Put that over x squared plus 1. Okay, and this equals, so 2 times half cancels out. It's just x over x squared plus 1. And then you do the same thing again. Sub in 1. It should give you the same answer. It's just 1 on 1 plus 1 gives you 1 on 2. It's a half. Okay, so there's another method to doing this. So this is just method 1. Alright, let's draw a line down here. Oh, oops. Let's try again. Draw a line down here. Yeah, alright. So the other method is if we do a u substitution. So then what that means, if we let, okay, so this is I'll just write here, this is method 2. Okay, so if you do a u substitution, we're saying let u equals x squared plus 1, because it looks ugly in the rest of the function. That looks the ugliest, so let's just simplify it down. So let u equals x squared plus 1. And then we have du dx. If you differentiate that in terms of x, it gives you 2x. Okay. So now you can rewrite f of x as log e of the square root of u, which of course can be rewritten using your indices laws, log e of u to the power of a half. Of course you can go again like this one right here and rewrite that as a half log e of u. This would actually be a lot easier to solve. It's your choice. You can also go straight from this function right here if you want. It doesn't really matter, just whichever way is easier for you. If we go from this one though, so dy du, which is the same as, yeah, so dy du, so differentiating y in terms of u, because f of x here we're saying is y. So that's equal to a half u to the negative half over u to the half. Okay, so then that's a half times u, so the top is u to the negative half. Then since divided by u to a half, it means minus a half. This is just indices laws again. So that gives you half times u to the negative 1, which is just 1 on 2u. If you use this version here, then same thing. So you would have just had dy, you would just had dy du is equal to a half times 1 on u, which is 1 on 2, which is 1 on 2u. That's because if you differentiate u, that's just 1, so it's just 1 on u. So the same thing. And then what you do is chain rule. So what you want to find in the end is f dash of x, and f dash of x is the same as dy dx, and dy dx using chain rule is the same as dy du times du dx. Okay, so we already know what dy du is from the above. That's 1 on 2u. Multiply by du dx, we found that too in the first line, where we let u equals x squared plus 1. So that's just 2x. Multiply that through, half and 2 cancel out, so it's x on u. Okay, sub the u back in. That gives you x over x squared plus 1. And note that this is the same as just our first method. We end up at x over x squared plus 1, which is good because that's what we expect. So what we have here is, let's move. Okay, so we have f dash of 1 is equal to 1 over 1 plus 1, which is equal to 1 on 2. Yeah, so it's the same. Both methods should give you the same answer. If not, you might want to double check your working out. So this is our first question. Alright, so moving on. So for this question, differentiate 4 times e to the 2x minus 2 times e to the x plus 1 over 2 times e to the 2x. Alright, so when you look at this and you see it's a fraction, the first thing you should be thinking of is quotient rule. If you don't remember that, I have it written right here in recall. Recall that, so the second one you see here, d dx of high over low, so that's quotient rule. If you don't remember, it's just written there. So low d high minus high d low over low squared. Alternatively, if it's easier, u on v. So let's just say the u numerator, v is denominator. Both functions, so that's just u low d high, so I'm just gonna, that's not written well, so low d, oh, here we go, so low times d high, low d high minus high, which is u, times d low over low squared, so that's just v squared. Right. Also, to be able to differentiate that, you need to know how to differentiate exponentials. So we have it on the first line of recall, d dx of e to the power of a random function, let's say f of x, is equal to f of x differentiated multiplied by e to the f of x. So e to the f of x is still the same, but you have to multiply it by the differentiated f of x. Okay, so let's start this. Let's just say that's equal to y. Okay, so dy dx. Okay, so let's start off. So low d high. So the lower function 2e to 2x differentiated have the high numerator differentiated. So your exponential, so 4 times e to the 2x, that is 4 times 2x differentiated, which is 2, and then e to the 2x. The 4 at the front is a constant. You don't have to worry about it. It's not going to affect your differentiation. And then minus 2 times differentiated of it's differentiation of x, which is just 1. So it's just x e to the x. And then plus 1. 1's a constant. So that's just 0. So that's nothing. And then minus. So that one was low d high, and then high d low. So the higher one is, I'll just copy that whole thing down. 4e to the 2x minus 2e to the x plus 1. And then multiplied by d low. So differentiation of 2e to the 2x. That is just 4e to 2x, because 2 times 2. Put this whole thing over low squared. So 2e to the 2x squared. Okay. Now let's just expand this through. Right. So that's equal to 2e to the 2x. Alright, so what's in here? 4 times 2, so that's just 8 e to the 2x minus 2 e to x. You can't do anything with that because e is to the power of x here, e to the power of 2x there. You can't collate them. Minus, alright, so for e to the 2x here, you can rewrite as 2 times 2e to the 2x. So I'm going to write 2e to the 2x and then times 2. That's just the same as 4e to 2x. I haven't changed anything. And then rewrite that. What's that in brackets? So 4e to the 2x minus 2e to the x plus 1. Okay. And then this whole thing over. So what is 2e to 2x squared? You square the 2, so that's 4. And e to the 2x, so e to the 4x. No, wait, actually, I'm just gonna leave this as 2e to the 2x times 2e to 2x for now. You just see in the next step why I'm doing this. Because you can actually see here, if I use a different color, so it's just easier to tell. The 2x in the numerator can cancel out with the one on the bottom. So when you're cancelling out on a fraction, you have to take into account that every single variable, every single value has to be able to factor out that one number that you're cancelling out, which is 2e to 2x, which is why I wrote 2e to 2x times 2 bracket blah blah blah. So we should be able to simplify this much better now. I'm just going to change back the color. So this one will turn out to be so dy dx. We cancelled out the 2e to 2x, so it's just 8e to the 2x minus 2e to the x minus, okay, so 2 times 4e to 2x is 8e to 2x. I'm just going to put a bracket around here because there's a negative sign in front of that too. Be careful, don't forget that negative sign. Then 2 times negative 2e to the x is negative 4e to the x. And then 2 times 1 is just 2. Alright, and then this is over 2e to the 2x. Let's keep going. So let's get rid of that bracket there. So 8e to the 2x minus 2e to the x minus 8e to the 2x plus 4e to the x minus 2. And this whole thing, once again, over 2e to 2x. Now, you probably already noticed by now that you can cancel out the 8e to the 2x with that one. And then what we'll do is collect like terms. Negative 2e to the x plus 4e to the x is just 2e to the x minus 2 to e to 2x. You can simplify this down to e to the x minus 1 over e to the 2x. We just divided the whole thing by 2. If you don't see it, I'll just rewrite it here. 2 bracket e to the x minus 1. Okay, so just factorize the 2 at the top. And over 2 times e to the 2x. And then you can just cancel out these two. So that gives you e to the x minus 1 over e to the 2x. You can't simplify that. Yeah, unless you want to put them into two fractions. It's completely fine to have it like this. There's no problem. And since they just told you to differentiate it, they didn't give you any initial conditions. So they're just asking for a general solution. And then, so this is your general solution. All right, on to the function questions. So question 3. We have an unknown domain within the subset of R, so real values. And the function is f of x is equal to 5 minus x with a range of negative 2 to 3, where negative 2 is inclusive and 3 to x equals 3 is not included. All right, so if you're ever stuck on a question like this and it looks too complicated, break it down. I would recommend you first draw a diagram. It always helps. So let's look at f of x is equal to 5 minus x. Ignore the range, ignore the restrictions. Let's just draw it as if all the values are included. So I'm just going to draw the axes here. Just a quick sketch will do. So x and y axes. And we have 5 minus x, so that's a negative gradient. And it goes plus 5. So if we were to rewrite this as mx plus c, so it's negative x plus 5. So the y-intercept is 5 with a gradient of negative 1. So let's just say it's something like that. Straight line, of course. All right, so that's the origin. So this value right here is 5, 0. And the y-intercept, 0, 5. So we have an idea of what the graph looks like at least. Now, if we were to sub in the values given to us from the range, we know that f of x, so if we sub in negative 2 first, so if f of x is equal to negative 2, this is the range, so it's saying that, before I said that x is equal to 3, I meant y is equal to 3, my bad, because this is the range, so y values, negative 2 to 3. So f of x is equal to negative 2. This implies that 5 minus x is equal to negative 2. Now just simple rearranging, we know that x is just equal to 7. So if we write that in coordinates, that's 7, negative 2. Okay. Note that these are coordinates, so even though they're two inclusive, you're using a square bracket. But because we're talking about coordinates, so they're just curved brackets. They don't actually mean inclusive or exclusive or anything. So f of x, so if we sub in y value equals 3, this implies that 5 minus x. So that arrow there, by the way, it just means implies. Yeah, so 5 minus x is equal to 3. So x is equal to 2. Rewrite that as coordinates, 2, 3. What is the domain? You can actually find a domain without even needing to graph it at all. Really, you've got your answers right there. Your domain is equal to, so 2 to 7. Now which one's inclusive, which one's not? You can just see, so the one where y is -2 is included, so that's 7's included. Y equals 3 is not included, so that means x equals 2 is not included. So 2, 7, 7 is, oh, okay, so where 7 is included. If you want to graph this, so you have a better understanding, oh, oops. Okay, so we're going for domains 2 to 7 is negative. You can already tell from the first graph. So, and it goes down to -2. Right, so not drawn to scale, obviously. Probably looks something like this. Oh, let's just redo that. It's pretty bad. Trying to draw straight on a laptop. Whatever, you get the idea. Okay, so then this end is open, this end is included, but this one is 2, 3, and this one is 7, -2. Okay, so you can tell here that if we go from the range -2 inclusive to 3, the domain is 2 to 7, where 7 is included. So don't be confused just because the range, the left end of the range interval is square brackets. It means that your domain, the left one, has to also be a square bracket. It depends on what your gradient is because the gradient's negative here, so it's the other way around. Draw the diagram if you need help. Diagram always helps. Okay, last question. Which one of the following is a possible domain for the function f of x equals to this x plus 3 squared minus 6, a quadratic, if the inverse function is to exist? And then we have multiple choice. So option A, all the real values. B, from -6 inclusive to infinity. C, -infinity to 3 inclusive. D, 6 inclusive to infinity. Or E, -infinity to 0. So to be able to do this question, you have to know what inverse function is. What does it mean for it to exist? What's a function? So a function is if a polynomial, an equation, is 1-to-1 or many-to-1. So 1-to-1, if in case you don't remember, something like a linear, that's 1-to-1. So one x value for one y value, or many-to-1, so such as many-to-1. An example of that would be okay. An example of that would be quadratic. Quadratic is many-to-1. You can use the line rule if you draw a vertical line test here. Vertical line test, it should only go through one. So every x value should only go through one value, y value here. If you do the vertical line test, yes. However, for an inverse function to exist, this function cannot be many-to-1. It has to be 1-to-1, because if you were to find the inverse of a quadratic, it would become like that. And that one would be 1 too many. If you do a vertical line test, one x value, too many y values. And we don't want that, because in inverse, that wouldn't be a function if it's many-to-1. It'd be a relation. So let's just remove all that. Okay. So start of this question, once again, you can graph it if it makes it easier. I would recommend you graphing it. In this question, you don't really need to worry about the intercepts, because we're just looking for whether the inverse exists. So we're looking for where in this function, f of x, will the function, when you restrict the domain, when will it be 1 to 1? Okay, so I'll just quickly graph it so you get an idea. All right, so turning point is -3, -6. You can just tell from the graph, where that's h, that's k. So -3, -6. I've worked this out beforehand, but it goes like something like that. Excuse the graphing. -3, -6. Okay, if you want to know, okay, so this should be a line of symmetry going down here. All right, these intercepts, you don't actually need to find them out, but if you're curious, the x-intercepts are -3 plus or minus 6, square root of 6. You don't need to find them out once again. If you do want to find them out, just make y equals 0 for that. Okay, so we want the inverse of this function. And before we mentioned that the function has to be 1 to 1 for an inverse to exist. If it's a quadratic, it's going to become a relation if you don't restrict the domain. So in order to restrict the domain, what we want is either to take just this left-hand side, or we take just the right-hand side away from the line of symmetry, because from the turning point, if you go one way or the other, it will be a 1 to 1 function. It's sort of like if you were to find the inverse of that, it would go something like that. And you're either taking only, so that's your point here. So if you were to find the inverse, it would be -6, -3. So what you're doing is you want to either take this top part or you take this bottom part. Because if you don't restrict it, then you're going to end up using your vertical line test. You're going to have two values. That's why you have to cut it down the line of symmetry. Okay, so what is this value? We know that the x value here, just looking at the first graph we drew, is -3. So a 1 to 1, we can restrict the domain in many ways. If you take just the left side, it would be from, so domain would be from -infinity to -3. Alternatively, you can take the right-hand side. So that one's the left-hand side. If you want to take the right-hand side, that would be the interval from, oh yeah, this one's actually a square bracket, because you can include the turning point. The turning point only has one of that point. So -3 to infinity if you take the right hand side. Okay, so if you look at our options A, B, C, D, E, you notice that none of them actually match it. Don't be fooled by C, -infinity to 3. Our graph here is -infinity to -3. That's different. So don't pick that out of haste. So although you can take just the left-hand side or just the right-hand side, you can also take just a portion, just a part of the left-hand side or a part of the right-hand side. So it's not like you have to take -3 to infinity. You can take 0 to infinity. That would still be right, because if you go from 0, this point here, onwards, it's still 1 to 1. No one said that you have to take from the turning point onwards. So the only condition is that you can't have the left hand side and the right hand side included in that interval. You can't have a bit of both, because then you'd have two values, and that wouldn't be 1 to 1. It wouldn't be the inverse wouldn't exist as such. So we know immediately that this is wrong. It can't be all the values. We already established that all the values means you're going to have 2 points for 1 point. Okay, what about -6 to infinity? -6, x equals -6 would be like, well, it'd be on this side of the graph. So if we were to sub that in, -6, x plus 3, so -3 squared, 9 minus 6. 9 minus 6, 3, so it would be like somewhere here. So here onwards, okay, that's definitely 1 to 1. So we already know, yeah, it's B. If we keep on looking, just to eliminate the rest if you want to be sure. So C is negative infinity to 3. We already said negative infinity to 3, you're going to be here. That's passing, you started from the left-hand side, you went over to the right-hand side, you're going to double up on values, so that's wrong. From 6 to infinity, if you're going from 6 to infinity, oops. Sorry, B is not right. We're not looking at negative infinity to negative 6. We're looking at negative 6 to infinity. Okay, negative 6 to infinity, you're starting from the left-hand side, you're also going to right-hand side. Just like C, that's not right. Okay, D, 6 to infinity. Yeah, okay. So you're starting from the right-hand side, you're continuing to right-hand side, you're not crossing over to left-hand side. So this one's correct. Alright, E, negative infinity to 0. Our turning point's at negative 3. If you're going from the left-hand side to 0, you're crossing over to the right-hand side. So that's also wrong. Okay, so the answer is D. Okay, so that's all for today. That's the end of the 4th question. Hope that made sense. If you have any questions, you can ask me in the comment section below or private message me, whichever is easier. Sorry for the mistakes today, and I hope that this was helpful. I'll see you next time on the Bunnyhop channel.